were discussing about the recurrence relation and mainly the how to design the recurrence relation. Now, if we remember that when we have read the recursive algorithm, then some examples we have seen, mainly the Fibonacci sequence, that if we write the recursive algorithm to compute the nth Fibonacci number, we have seen that the recursive algorithm is not efficient, because it took much more number of additions than the iterative algorithm. But there are many examples, even the recursive algorithm is not efficient, then also we use recursive algorithm or recursion, since there are many problems where we can very simple way we can give a solution procedure. That means, we can give a algorithm. That means, the recursive algorithm is much easier to solve the problem. And we will see today this type of problems. So, first we read our Tower of Hanoi problems. So, again we continue the recurrence relations. And first we see some of the problems where how we can frame the recurrence relation. Then one such example is the Tower of Hanoi. So, Tower of Hanoi is a puzzle. First I explain the problem. So, it is a puzzle consisting of three pegs mounted on a board. And n number of discs of different sizes with holes in the center Now, it is assumed there is some restriction of placing the discs on the peg. That what is that restriction? That it is assumed that if a disc is on a peg, only a disc with smaller diameter can lie or can be placed on the top of a of the previous disk. That means always the smaller disk will be on the top. Now, the problem is to transfer the disks that are stacked on one peg to another peg by moving one disk at a time. And we can use the third disk for this purpose. Okay. So, this is the problem is this. So, first we will frame a recurrence relation for this. Then see, this is one puzzle, and solving this puzzle is very difficult if when n is very large. So, if I again explain properly, say I have 3 peg say this is first peg, second peg, third peg, and in the first peg the n number of disks are there. So, in this way I can draw say I have to shift all these disks from, the problem is to shift or transfer all the disks from peg 1 to peg 3, and we can use peg 2, and the restriction is, I should tell the restriction, that always lower discs or smaller disc having disc with smaller diameter. So, I can tell smaller discs will be on top. Even during the transfer we must follow this restriction. Now, see, if I have only one peg, then what I will do, that simply I will say I have only one peg, then simply I will transfer this thing to peg 3. So, I need only one move. Okay. So, if I write, then number of moves, it is 1. But if I have, even if I have 2, then also I have to, first I have to, if now say I have say I have 3 pegs, say I have 2. Then first I will move the larger one to 3, then the smaller one was the larger one here, then the smaller one into 2, then the smaller one from 2 to 3. So, I need one move, then it is 2 move, then it is 3 move. So, I have 1 move first here, 2 here, 3 move. So, now when the number of discs are small numbers, say 1 disc, 2 disc, 3 disc, then in this way we can shift that thing. We can transfer all the discs from one peg to another. But if n is a very large number, then it is very difficult to write this type of program, and if we want to write a program, then it is very difficult to write that thing. Then first thing is that how to solve, or what will be the number of moves required if all the disc I want to shift from 1 to 3. So, what will be the approach? So, to get a solution for this type of problem, actually recursive approach is very easy to understand and to represent. What we will be doing? So, our approach should be that if I have n number of discs, and already we have seen that for one disc it is very easy. When n greater than 1, we solve n minus 1 disc problem. What is that thing? As if we will transfer the largest disc here. So, I need one move for this, and these remaining n minus 1 disks, remaining n minus 1 disk, I give this number to shift. So, this is my for n minus 1 disk I will give, and then I have for this I have a larger disk here. So, as if I have a larger disk, and then I will shift this n minus 1 disk to here. So, again this is some n minus 1 disk moved to here. Then all n disks are shifted from 1 to 3. So, here actually I will be giving that as if these are my n minus 1 disks, and this is my the largest disk that was at the bottom of the peg 1. So, we solve n minus 1 disk twice, here 1 and here 1. So, twice and explicitly move one disk, that is the largest disk, so this will give me the solution. So, what is the recursive approach? We know that if n equal to 1, for n equal to 1, I need only one move, that already I have explained here. I need only one move, and our approach is, it is a recursive way of solving or recursive algorithm, that as if we solve n minus 1 disk problem twice, that means the largest disk is first moved to, or since at the top the first n minus 1 disks are moved from 1 to 2, then the largest disk is moved to 1 to 3, and the n minus disks are moved from 1 to 2, and the n minus 1 disks are moved to 2 to 3. Then we will be getting the solution that all n disks are moved from 1 to 3. So, this is our approach to solve the problem. It is, I think it is very much clear that if n is very large, even if it is n is 10, then it is very difficult to move this type of thing. Rather, as if we assume that when I have 10 number of disks, as if the smaller number of disks, say for 9, it is already solved. That means we can move in this way, we can do that thing. So, now how we can give the recurrence relation for this problem? So, the recurrence relation, that just now what I told, that we have to solve n minus 1 disk problem twice. So, the solution is, if we represent, let Cn be the number of moves required to transfer n disks from peg 1 to peg 3 using peg 2. So, now we can write the way we have given the solution, that Cn is twice we solve the n minus 1 to Cn minus 1, that means one explicit move. What is this 2 Cn minus 1? This 1 Cn minus 1, okay. You can write 1 Cn minus 1 is the number of moves to transfer n minus 1 disks from peg 1 to peg 2, and another Cn minus 1 is number of moves to transfer n minus 1 disks from peg 2 to peg 3. So, I can tell this is my 2 Cn minus 1. I can tell this is my 2 Cn minus 1. Okay. And this one is for move. This is my explicit move to transfer the largest disk from peg 1 to peg 3. So, this is this is my recurrence relation for tower of Hanoi problem. So, this is my recurrence relation, and it is very much clear that much easier way we can represent this thing. Then once I get this thing, and since I know the initial conditions also, what are my initial conditions? What is my C1? If I have only one peg, number of moves required is 1. So, C1 is 1. Now, I can get a explicit formula for this. So, I know the recurrence relation Cn is 2Cn minus 1 plus 1 with C1 equal to 1. Then I can write 2Cn minus 2 plus 1. So, plus 2 plus 1, then again this is 2 square Cn minus 2 plus 2 plus 1, then it is 2 cube Cn minus 3 plus 2 square plus 2 plus 1. So, in this way if we proceed, then we will be getting 2 to the power n minus 1 C n minus 1 plus 2 to the power n minus 2 plus 2 square plus 2 plus 1, because when we are getting 2 cube it is Cn minus 3 and it is 2 square. So, it is I am putting as n minus 1. So, this becomes n minus 1. So, this becomes 2 to the power n minus 1 C1 plus 2 to the power n minus 2 up to 2 square plus 2 plus 1. So, this becomes, since this is C1 equal to 1. So, this is 2 to the power n minus 1 plus 2 to the power n minus 2 plus 2 square plus 2 plus, that means it is I am getting that n number of terms, and this we know the answer, it is 2 to the power n minus 1 by 2 minus 1. So, this is 2 to the power n minus 1. See, we have started with the recurrence relation. So, this is my, just now we got the recurrence relation of solving tower of Hanoi problem. This is my recurrence relation, and just if I continue iteratively, then we get the solution also, and this is my explicit formula for the number of moves to transfer n number of disks from one peg to another. So, this is the solution for tower of Hanoi problem, or we can write that this is my solution of tower of Hanoi problem. And this is the solution. So, solution is one that it must satisfy the sequences. That means, if n equal to 1, if I get n equal to 1, that means only one peg, then 2 to the power n minus 1 becomes 2 to the power 1 minus 1, that is 1. So, we know that from peg 1 to peg 3 only one move is required. For n equal to 1, it is only one move. Say for n equal to 2, then 2 to the power 2 minus 1 is 3 move. We have already seen that if it is a 2, if we remember that, so if I have 2 peg, so one first the largest will go here, one smallest will be go here, and then again smallest will go here. So, I have 3 move. So, it satisfy the relation for any number of pegs. So, these will give me the solution. This is my solution of tower of Hanoi problem. And what we see that if I take the recursive approach or the recursive algorithm, then actually it is much easier to handle this type of problem. Now, we take another example. Let I have let there be n numbers. Then how many ways, the problem is that how many ways okay, and we have to first we write the problem. We have n numbers and we have to compute the product of these n numbers, say numbers are A0, A1, A2, say n minus 1. Okay. And then I can take n plus 1 number and I can put here n. Now, at the product at a time, product is done for two numbers. Say ai and ai plus 1. Now, the problem is that how many ways to parenthesize the product of n plus 1 numbers. We try to explain or with some example. Let there be 5 numbers. Or take phone numbers, then it will be easier to give that thing. Numbers, say A0, A1, A2, A3. Now, we can parenthesize to compute the product, like I can parenthesize A0, A1, then A2, then A3. Then I can do A0, A1, A2, then A3. I can take A0, A1, A2, A3 and then I take the product. I can take A0, then A1, then A2, A3, or I can take A0, A1, A2, then A3 first and then. So, these are the 5 ways we can parenthesize to compute the product. When we have 4 numbers A0, A1, A2, A3. So, my problem is that how many ways to parenthesize the product of n plus 1 numbers. Now, if we observe that the product or the parenthesizing the numbers when it is only 4, then we see that as if we take that we are solving the problems with a lesser numbers, then it is much easier to do that thing. Say we take this thing A0, A1, A2. So, as if A3 is the one number left, and this is that when there are 3 numbers A0, A1, A2. So, we first complete the product of these 3. That means, it gives that if 3 numbers are there instead of 4, then it gives that how many ways we can parenthesize, and then we add 1. So, if in this way we can do, then my solution will be, I can write my solution. So, let Cn be the number of ways we can parenthesize to compute the product of n plus 1 numbers. Okay. And just now we have seen that we have, if it is C3, like one example we have taken, that if it is C3 equal to 5 for n equal to 3. So, if some recursive approach we apply, then we can write that Cn is C0, Cn minus 1, as if only one element we have taken, and then C1, Cn minus 2, C2, 2 Cn minus 3 then the reverse order n minus 2 C1 Cn minus 1 C0. Again we just see the way we have done A0, A1, A2, A3 and this is the way we have taken it A0, A1, A2, A3, the reverse thing. Similarly, here it is a reverse and this is only one, that is 0, A1, A2, A3. So, I can write this thing as sum of k equal to 0 to n minus 1 Ck and C n minus k minus 1. So, this gives a recurrence relation. So, already we have seen that for n equal to 3, that C3 equal to 5. So, we can put here that n equal to 3. So, what is my C3? So, my C3 is k equal to 0 to 3 minus 1 is Ck Cn minus 1 is C2. So, this gives me that is C0 Cn minus 1 and that gives me the 10 minus n minus 1 n minus k minus 1 I write. So, first thing is that k equal to 0 and n equal to 2. So, this becomes 2 minus k minus 1. C0 C1 plus C1 C0. Plus C2 C0 C1 plus C1 C2. So, we can get in this way we can actually satisfy that our solution must satisfy the recurrence relation. So, what we have read in this lecture that we see that some of the problems like Tower of Hanoi problem or this parenthesizing numbers to get the product that recursive approach is efficient in that sense that recursive approach to get or to solve the problem is easy to understand. And even for it is much difficult to write algorithm iteratively. So, we have seen that some examples, particularly tower of Hanoi problem we have seen. An approach is first we will apply some recursive approach, then we find out the recurrence relation, find out a recurrence relation. We have seen that how to get the recurrence relation, and next we will be, for some simple examples we have shown that how to get the explicit formula, which is nothing but the solution of the recurrence relation. So, the next is to get the recurrence relation or get an explicit formula for the recurrence relation. Which is nothing but the actually the solution of the recurrence relation. So, now we learn that how to solve the recurrence relation. So, in this class we have read how to frame or how to design the recurrence relation for a given problem, and to get the solution we have to learn that the different techniques that is used to solve the recurrence relation.